So in today's video, we're going to go ahead and cover the second fundamental theorem of single variable calculus. And in the past, we looked at the first fundamental theorem and its applications, especially when understanding kind of the formal definition of an accumulation function. Now we're going to delve into the second fundamental theorem, which really is going to assist in evaluating definite integrals, as we're going to come to find. And so we're not really going to delve into the proofs of either of these two theorems just yet, but maybe towards the end we will. I mean, the proofs are not that crazy or intense. It just requires a little bit of knowledge from differential calculus. But for now, let's kind of just focus on actually stating these theorems and how we can actually apply them in different contexts. So suppose we have a function f of x, capital F of x, that's defined as the definite integral from c to x of f of t dt, and this is a lowercase f of t. And we don't really care what c is, right? That's just some arbitrary real number. And kind of another way to state this from the first fundamental theorem is that capital F prime of x is equal to lowercase f of x, right? That's just equivalent. These two statements are essentially equivalent if we want to go back to the first fundamental theorem of calculus. And so the second fundamental theorem tells us that the definite integral from a to b of f of x dx is just going to be equal to capital F of b minus capital F of a. And notice here we just used f of x dx, and we just have two real valued boundary points from a to b, right? And so essentially this tells us that the definite integral of a function is just essentially given by the antiderivative evaluated at the two endpoints and the difference between those two endpoints. So capital F of b is just the antiderivative evaluated at x is equal to b, and then we're subtracting capital F of a, which is just the antiderivative at x equals a. And so another way to write this is just capital F of x, and then we put this line right over here, and we put the two endpoints from b to a, and it kind of indicates that that's f of x, or capital F of x evaluated at b subtracted from f of x evaluated at a. Right, so these are just two different notations. You can kind of use either one, whichever you prefer. So like I said, we're going to delve into kind of the proof of this a little bit later on. And it's a little bit easier to actually understand this theorem if we apply it to a couple of examples, which is exactly what we're going to do. And so suppose we have a function, capital G of x, right over here. So let g of x equal to the square root of 5x minus 1, such that g prime of x is equal to, or capital G prime of x is equal to g of x, is equal to lowercase g of x right over here. And then we're asked to evaluate the definite integral from 1 to 34 of lowercase g of x dx. And so since g prime of x, or since capital G prime of x is equal to lowercase g of x, then we know that this integral right over here is just going to be capital G evaluated at the endpoint. So g of 34 minus g of 1. So that's equal to the square root of 5 times 34, which is what? That's 170, minus 1. And then we're going to subtract the square root of 5 minus 1. So that's going to be equal to the square root of 169, which is 13, minus the square root of 4, right, which is 2. And so the final answer is going to be 11. And so we can see that it's actually not that bad of a theorem to apply. You just have to recognize the form. You have to see that here we have lowercase g of x, and we have its antiderivative defined above. I mean, we said that the integral is essentially just the antiderivative. That's another sort of interpretation of what an integral is. It's the antiderivative. And so when we're taking the integral of a function, the definite integral of a function, and we're given what that function's antiderivative is, like capital G is the antiderivative, then we can use that to evaluate the definite integral. And it just turns out we evaluate the antiderivative at the endpoints and subtract them. So let's do another example. Here we have capital H of x defined as 7 sine of pi x over 2, right? And then we have h, or capital H prime of x is equal to lowercase h of x, and we're finding the definite integral from 0 to 3 of lowercase h of x dx. Again, this is the same format. We have the antiderivative of a function, and we're asked to find that function's integral, so our definite integral. And so let's go ahead and actually do that. This is just going to be h of 3 minus h of 0, right? We're going to evaluate at the endpoints, and then that's going to be what? 7 times sine of 3 pi over 2, and we're going to subtract 7 sine of just 0, right? And we know that sine of 0 is 0, so this is just going to disappear. And so 7 times sine of 3 pi over 2, sine of 3 pi over 2 is -1, right? So this is going to be Oh, okay. That's going to be -7, and that would be our final answer. And so, we interpreted the definite integral as the area under the curve, and we ended up with a negative number. And that's something that we're going to examine in another video. Perhaps in the next video, we're going to look at the properties of definite integrals using this new sort of definition and ability to solve definite integrals with the second fundamental theorem of calculus. So I hope that this kind of clarifies how we can actually use this theorem and why it's very important.